Okay. Okay, so good afternoon, everyone. This is the UCL undergraduate math colloquial, and this is the first session for the school for the academic year between 2022 and 2023 and 2024. And the topic is rate reflection and rational approximation. It will be a discussion that connects two areas of mathematics that appear to be something very separate, but the connection will ultimately be seen as something that is actually quite beautiful. And it's a connection between physics and number theory. So this is something that belongs to the study of light, the optics, and this is something that belongs to the study of number theory. Rational, by rational I just mean the rational numbers. By approximation, I mean approximating an irrational number by a rational number. And we will show in this talk that these two areas are connected in a very interesting way. So let's talk about rate reflection. If we have a smooth surface, for example a mirror, and then we have a beam of light, say shooting in this direction, and we know that it reflects. So first it shoots in this angle, and then it reflects in the other angle. And the law of reflection tells us that these two angles should be the same. That's the law of reflection. Yeah, that's the first prerequisite knowledge, and it's there, and that's enough to understand the first part of the talk. So instead of considering like reflecting along one surface, we consider reflecting in a closed surface, namely a square. So we consider this to be a square, and you can use whatever length you want because all we need is just some scaling. So let's say this is a square of unit length, and we consider a light beam. So this is the starting point, and we just shoot in some random direction, say in this direction. So it reflects first according to the law of reflection. It should be something like, it should go somewhere like this, and then it reflects again. The basic idea is that it just keeps reflecting, and we want to study the behavior of the reflection. And in some certain cases, for example, if the angle of entering the mirror is the angle of incidence is just 90 degrees, then you just keep reflecting between two sides of the square, and that will give you a periodic path. So that's the periodic situation, and we also have the non-periodic situation. So let's write that down. So the first case is periodic, and the second case is say non-periodic or chaotic, if you prefer that. And in the first part of the talk, we are going to determine a condition to determine whether the path will be periodic or not. And it turns out that the condition is independent of where the light originally starts. It only depends on the angle. And we will see that in a moment by studying this problem using a very interesting method. The interesting method is that instead of studying the reflection of the light inside the square, of course you can, but you just need to pay attention to reflecting the path of the light when it hits a wall. So instead of doing doing the direct method, we consider that when the light is, we consider the situation before the light is hitting the first wall. So before it hits the first wall, we consider that instead of making the light reflect, we reflect the square room. We just draw another, okay, let me change it. We just draw another reflected square room so that when it hits the wall, because of the law of the reflection, we know the reflection angle is the same as the incidence angle, so we can just continue drawing this straight line. So it's actually an image of the actual reflection. But we just need to know that we have a reflected area on the right hand side. So we can keep track of this, and then we just keep drawing the light. And then we need to draw the corresponding extra square to keep track of the reflection. So we are going to study the light using, study the reflection of light using this method. And this actually gives us a very convenient, this actually produces a very convenient proof of that condition to determine whether the path is periodic or not. So now that's everything we need for geometry. Like that's the geometric aspect. And to study those geometric problems, we use algebra. Algebra, the advantage of algebra is that it's precise. You look at the expression, once you know how the expressions are related to the geometry, you just need to manipulate the expression and then obtain your results. So let's say that let's assume that this is the P0. That's where the light starts shooting. We record this point. We call this point x0, x0, y0. That's just the coordinates. And under this projection, well, since we have an initial position, we also need a velocity. We assume that the light travels in constant velocity, so let's say that the velocity vector is, say, vx, vy, just indicating the velocity component in each coordinate direction. So if we do the setup, then each point, say after t seconds, say this is the point after t seconds. If that is the point after t seconds, we have the coordinate being x0 plus t times vx and y0 plus t times vy. This is just the linear function because we already know that after reflecting the square root, the light just becomes a line. And in order for the light to actually produce a periodic path, we need to ensure that the light eventually hits the starting point. And it hits the starting point with the velocity parallel to, with the velocity being the same as the velocity, in the same direction as how it started. Like it needs to hit the point and also needs to be in the same direction. And a sufficient and necessary approach to study this behavior is to find a reflected P0 in those other extra squares, and then we just need to detect whether the light is hitting the image of the reflection. Okay, so like when we need to keep track of other squares, sometimes this P0 is reflected, but sometimes in other cases it is not reflected. And the reflection can only happen in two ways. One way is to reflect along a horizontal using like about a vertical line of symmetry. Like it either reflects on the vertical side or along a horizontal side. And sometimes to the left direction and sometimes to the right direction. But what we need to know is that after two reflections along the same side, like along the same orientation, it gives you the original coordinates. What I'm trying to say is that if this is after the first reflection, you get this P0, say prime, P0 prime. This is a reflected image. But if you do the reflection twice, yes, this is the second image, but the distance, like the coordinate of P0, with respect to the same square, like inside the square, it should be the same as the coordinate of this. Or in other words, like if you want to use like describe this technically, you can say that the coordinate of P0 and P0 double prime is the same modulo square. Like if you consider the difference between the coordinates. So this is exactly P0 shifted to the right by 2 units. And so this means that this actually has the coordinate of x0 plus 2 and y0. Yeah. And similarly, we can say that like after 2 vertical reflections, reflections along horizontal axis, if we perform the reflection twice, we also get an effect of shifting the original points by 2 units. For example, if we consider this P0 prime prime. So after reflecting once, you get a reflected one, so that's 3 primes. And then we can do another reflection, and that gives you 4 primes. And as we know from our discussion here, we know that the coordinate of this is exactly x0 plus 2 and y0 minus 2. So this actually means that the square, the entire square, is not reflected. It's only translated. Yes, I mean this square. So this square, like although they are in different positions, it's not reflected. It's the same as we just translate the square by 2 units to the right and 2 units downward. So it's the same square. So if the light happens to hit this type of square in the same direction, then we can conclude that the path will be periodic. Yeah, because the square has the same orientation. That's the word. It has the same orientation. So if the light is hitting the square in the same direction, it just means that this light eventually reflects from this wall and goes back to P0 and travels through the path again. So that's the geometric bit, and we may erase this part. So we can also express the same thing using algebra. We only shifted 2 units, but if we let k be any positive integer or any integer, and then we shift by 2k units, it's the same principle. So this means that the path is periodic if and only if there exists some time, well, strictly greater than 0, because t equals to 0 is just the origin, it's just the starting point. We need to exclude that. So there exists some positive time such that x0 plus t times vx is equal to x0 plus 2m. This means that it hits the original point's x coordinates in a translated square. And we do the 2. The appearance of 2 here is because it's the image is reflected when we only translate by like all the units. So we had to translate by even units in order to get the original point. And similarly, we have y0 plus t times vy being equal to y0 plus 2m, and m and n are just some integers. Remember what I said before? I said that this condition has nothing to do with their starting point, because we can cancel the x0 and y0 out. So after the cancellations, it just means that t times v of x is equal to 2 times m, and t times v of y is equal to 2 times m. So what this means is that suppose that the v of x and v of y are both non-zero. Because when one of them is 0, you get a horizontal line or a vertical line. And if both of them are 0, the light is not even moving. So we just exclude those situations. So this means that we have three cases. V of x or V of y is 0, and if all of them are non-zero, we can compute the quotient because t is greater than 0, so we don't need to worry about zero division. And this means that m and n are also non-zero. So the second case is that V of x over V of y is irrational. It's a rational number because m over n is a rational number. So you can gradually realize how number theory is entering physics. The light is periodic if and only if the ratio of the velocity is a rational number. And this ratio is actually very important because it is related to the angle of incidence. It's related to this parameter. Like you can use the ratio of the velocity to eventually tell some information about this angle. And if you do the calculation, you will find that it's related to the tangent of this angle. So what we have proven here is that the path of the light reflected in the square produces a periodic path if and only if the tangent of this certain angle is a rational number. So that's how everything becomes connected with number theory. So that actually finishes the first bit. So what we said is that V of x, Vx and Vy, when multiplied by the same constant, becomes an even integer. So we can also translate this condition to saying that n times V of x minus n times V of y is 0. So are you okay with these two equivalents? So if we multiply V of x by n and then multiply V of y by n and use this relationship, we can arrive at this expression. And we can also produce this in the other direction. So this means that we can find two integers such that the linear combination gives you 0. And the integers are non-zero as well. Like not all of the integers are 0, which means that not all 0. And by the way, have you learned about the linear independence in algebra? So this means that Vx and Vy, they are linearly dependent over integers. So this is just a way to express this statement using linear algebra. So Vx, Vy, linearly dependent over integers, over z. So we can write the condition here. Periodic if and only if Vx, Vy linearly dependent over integers. So that actually finishes the first part of our talk. And so we can now talk about the second case. And the second case is the most interesting case because we don't have this linear dependence. We are talking about the situation where everything is not periodic. And as we learn from all our experience about non-periodic things, it's always chaotic. And we will show in a moment that this chaotic thing is actually very interesting. And we can generalize this chaotic behavior in like higher dimensions as well by using a essentially similar function. Okay, so we still remember that this is the starting point, and this is the velocity. But because we are investigating the non-periodic case, we also need to specify that Vx and Vy are linearly independent over integers. This means that if you want to solve the equation a times Vx plus b times Vy being 0 for for some integers a and b. This implies that a and b both have to be 0. That's the meaning of linear independence over integers. And you can replace these integers with anything, like if you want to talk about the definition. Like this is linearly independent over z, but if we say linearly independent over q, then that can be replaced with rational numbers. But we just talk about the special case, and that's enough to cover the topic. So what we are going to prove is that when the path is not periodic, let's first draw a non-periodic path. So we have this. Suppose that we have this is the starting point. It reflects, it reflects, it reflects. It just keeps reflecting, and you can actually see that the reflection is likely to fill in the entire square. It's gradually filling the entire square, because this is not going to be periodic. When it's periodic, it eventually goes into a loop, and then there will be a lot of spaces left inside the square. By space, I mean that an open set, which means that you can draw a tiny ball, tiny circle inside the set. So that's what I mean a space. It's a set. Or just a small circle, but that's just my way to prefer saying that. And you will learn in the future that this is something known as the open set. So what I am claiming here is that if the path is not periodic, then after infinitely many seconds, like if you like plot all the points hit by the light inside the square, then it leaves no space. So it means that if you draw any tiny circle inside the square, it's going to touch at least one point, because you can shrink the circle as small as you wish. It actually touches infinitely many points. So that's how chaotic the non-periodic path is. And let's start proving this. And that will be something that combines calculus with number theory, which is another surprise because they seem to be very disconnected from each other, but they are. So before showing that every space inside the square always covers a point hit by the light, let's consider the origin. Since we know that the periodic path, they need to hit the P0. So what happens now is that we want to draw some circle around the P0. And we want to prove that like this circle always covers infinitely many points hit by the light. Like how small, no matter how small the circle is, it always hits infinitely many points hit by the light. But just for some caution, we need to exclude this part because this is where the light starts shooting. We need to exclude this because otherwise this automatically like covers everything, because you can always find infinitely many points from a light second. So we consider the following problem. We define the set. Say this is the S subscript T. This actually just means that the point hit by the beam of light after T seconds. After T seconds, which means that we just remove the first few, the line segments that are in the path of the light in the first T seconds. So if we introduce this quantity, when this T is sufficiently large, we can get rid of this line segment. So that will make all our investigation meaningful. And the result we want to prove is the proposition that is the claim that for every large T, as long as it's finite, just some positive number, say 100, 1 million, or like 1 trillion, whatever you want, or like 1 Googleplex, but it's a finite number. For any finite number t, the set ST leaves no space inside the square. And if you're familiar with analysis, this is equivalent to saying dense. So, also known as dense in the unit integrals Cartesian square. That's just a mathematical statement, and you will become familiar with this kind of language in the future because it's much shorter than this description. So we consider after t seconds, this bit is gone. But I am claiming that, like, you can see that there are some other lights that are shoot inside the circle, and we are going to prove the existence of that phenomenon. So we know that when a sufficient condition for a point to be hit by the light is that, so let's say that this x1, y1, this is just a generalization of our study of the periodic case. In the periodic case, we take x1, y1 to be the original point, to be the starting point. But here we just generalize the statement, and we can see that this is actually not the sufficient and necessary condition, because it is also possible that a light hits the point in a reflected square, but not the translated square. I remember the even units and the odd units. Like in the odd case, it actually is a reflected. We need to do a reflection. But for simplicity, we just only work with the translated case. So there's a subtle difference, but it's not a big deal because this, like just working in this case already produces some very marvelous results. So we just need to, so we can actually forget the picture. Just remember this algebraic fact. We can just study this problem using the statement. So we don't need to look at the picture. And the rest of this session will be about how to play with this statement and get the interesting result here. And so if we use the notation here, we can actually formulate this statement in a more mathematical fashion. So x1 and y1 belongs to the to st when we can find n integers and some t greater than or equal to the capital T, such that this happens. Any problems, questions about this bit? Okay, so I understand that it's so many information in a short amount of time, but yes, feel free to ask if you need. All right.
I would allow any T to be equal than or greater than and greater to than.
Okay, for this, it's actually not very significant, but yes, but we just use the weak inequality here.
Yeah, just so you keep in mind the where can hit the same point many times, right?
Yeah, so it's actually infinitely many times. So this is this ultimately becomes something that is not too important. So yeah, let's continue. This is so we have this condition now, so we don't need to worry about the picture anymore. So if we want to do the weaker claim that that this ST always contains points that are very near the starting point E0, which means that for every epsilon, you know this very well. For every epsilon, there exists some point, and for every t greater than 0, there exists some point x1, y1 inside the set ST, satisfying the inequality that the distance between their x coordinates and the distance of their y coordinates are all less than epsilon. So this is technically not a circle; it's a tiny square. But for any non-empty circle or non-empty square, you can always fit a circle inside a square, and you can also fit a square inside the circle. So we are actually working with squares, but just for some amusement, we use circle, but they're equivalent in geometric sense. Since it's two-dimensional, it's not something that are too different from each other. So we want to prove this statement, and after proving this statement, we can generalize. So if we replace this x0 and y0 with any point inside the square, we will establish this claim. But now we just work with the special case. The special case has a very straightforward proof, and it's proven using the pigeonhole principle, and we will show you in a moment how simple this is compared to the general case. So remember this. So let's look at this statement. So suppose that okay. So this means that if we can replace the second x1 and y1 to be something that is less than epsilon. So all we want to do is that this x1 and x0, we can move this expression a little bit. We can minus x0 into the right-hand side so that tvx minus 2m is equal to x1 minus x0, and p times vy minus 2 times n is equal to y1 minus y0. So as long as we can find a point t such that these two integers m and n such that these two quantities are less than epsilon, we are done. Like if the distance, if the absolute value of these two numbers are small enough, we can actually establish this claim, because we know that x1 and x0, the distance is exactly the absolute values of these two quantities. So we can see that we are actually multiplying some number by a real number, and then we want this to approximate some integers. And this is the typical question studied by number theorists working in the area of rational approximation. So that's where the approximation comes. So let me see if we can erase any bit here. So since we have already finished up the periodic case and we are already analyzing the non-periodic case, we can just say that we can use this little bit of space. Since we want to prove this theorem, we don't need to work in two directions. We can just look at any sufficient conditions, and then once we prove the sufficient conditions, we prove the statement. And we know that this is a sufficient condition for a point to lie inside ST. And then this is a sufficient condition to find that point and then make it satisfy this proposition. I know that there's a lot of information here, but that's the direction we are going to work with. So what we are doing now is that we want to find the number t and the integers m and n such that these two quantities are small enough. So yes, we can remove the definition of this. So the idea is that we consider the quantity fractional component. have you guys heard of this function, the flow function? Like if you throw pi into the flow function, you get 3. And if you throw pi into the fractional part function, you get pi minus 3, because 3 is the integer part of the number. And similarly, the flow function like gives you the largest integers less than or equal to the integer itself, even when the number is like 4.9. When the number is 4.9, the flow function is 4. So the fractional part is 0.9. And we are going to investigate this function. We are going to investigate this this function Vx times k. We investigate this this function, and from the definition we know that this is always greater than or equal to 0 and strictly less than 1. Because when it cannot be 1, because like when it's 1 you get an integer, and that actually leads to some contribution. So it's actually greater than or equal to 0, but strictly less than 1. And so now we consider this function, and we let k to be some number that is ranging from 0, t, 2 times t, all the way up to n times the square of n times t0. This n is just some large integer. Some positive integers. And yes, this is this actually gives you like n squared plus 1 points inside the unit interval from 0 to 1. And now we consider the two-dimensional point. So if we consider this point, the point formed by this in this manner, and we throw in these many distinct numbers, we actually get n squared plus 1 distinct points. Not necessarily distinct, but just different points. Okay, doesn't mind if I remove this definition. Like if you remember have you remembered the definition of ST, which means that it's the set of points hit by the light after t seconds. Just remember it's something that happens after t seconds. So these are n squared plus 1 points inside the unit square, except that the 1 bit is the open not closed. Any issue with this part? Okay, so now we are going to partition this into smaller bits. We want to partition this larger unit square into some squares of side length 1 over n. And if we want to fit as many squares of this fashion into the unit square, you are going to have n squared amount of squares. Because well, that's just about the area. Like if you consider this 1 over n as the unit, then there are n squared of them inside the actual unit square. So there are n squared of them. So what we are doing is that we are trying to put n squared plus 1 points into n squared amount of smaller squares. So let's consider a simpler problem. Now you have 5 apples, and then you have 4 boxes, and you are going to put all 5 apples in 4 boxes, and then at least one of the boxes contains 2 apples. That's the pigeonhole principle, and we are going to apply that principle here. So we have n squared plus 1 points, and then we have n squared smaller squares. Then the pigeonhole principle tells us that there are at least 2 of them lying inside the same square. And lying inside the same square can be expressed as having their coordinates difference less than the side length of the square. for example, if 2 points lie inside the same square, then the difference between their x coordinates and the difference of their y coordinates will be strictly less than the side length of the square. And because we have considered the interval to be one of them being closed, one of them being open, we don't really consider the case where both of the points are lying on the boundary. So the side length are strictly less than the difference are strictly less than the side length of the smaller square. This means that there exists some points 0 less than k1 less than k2, and the whole thing is also less than or equal to n squared times t0. So there are 2 points satisfying the condition that Vx k1, k2 minus Vx k1, this thing is going to be less than 1 over n. Okay, I'm going to remove this bit. So we can also express this using the definition again. Like the fractional part is just a number itself minus the flow function of itself. So this means that the whole expression is going to be v of x times k2 minus k1 and subtracted by some integers because it's a difference of flow functions. And let's just call this integers p, and this thing is going to be less than 1 over n for some integers p. Any problem with that? Okay, and now we are going to do some substitution here. Because k2 is strictly greater than k1. So the difference will always be less than the difference between always greater than or equal to the difference between the consecutive case. So this means that this k2 minus k1 is going to be strictly, is going to be greater than or equal to the number t. Because that's the way we choose them. Yeah, that's t. So what we want to do here is that, let's say that we record this t to be 2 times k2 minus k1. Why we multiply this by 2? It's mainly because we want to make sure that they are approximating an even number. So we actually need to multiply both sides of these by 2. This means that v of x times t minus 2 times p is going to be less than 2 over n. So now we have this inequality. And because the way we choose the integer p and k2 and k1 are solely dependent on the number n. And this n can be made as large as we want. And we can make it so large such that this 2 over n is less than epsilon. So this means that if we organize the reasoning here, we can choose a arbitrarily small epsilon and an arbitrarily large t, since there are no restrictions on t here, so it's also an arbitrary number. So arbitrarily small epsilon, arbitrarily large t, and then we can find some k2 and k1, which gives you a gives you a choice for the smaller for the small t, such that this inequality is going to hold, and this inequality is going to this thing is going to be less than epsilon as well. And the same reasoning tells us that this vy t minus 2 times q is going to be less than epsilon as well. And if we just trace all the reasoning back, we have this thing proven. And we can actually generalize this principle. And after generalization, what you get is essentially the Dirichlet's approximation theorem. So if we let like x1, x2, all the way up to x of n to be some real numbers. And this actually means that for any natural number, for any positive integer n, there exists some, and also for every real number t greater than 0, there exists some t which is greater than or equal to t and less than or equal to the less than or equal to n to the nth power times t. And there exists some integers y1, y2, ym in integers, such that the inequality t times xm minus ym is going to be less than 1 over n for any for all of the m. So 1, 2, 3, all the way up to the capital N. So this is the general approximation theorem. Instead of working with the square, we work with a n-dimensional hypercube to get this sorted. And the interesting case for the Dirichlet's theorem is that when we consider one variable, that is to say, when we reduce the square to a line segment, then it gives you something that is really something concerning the rational numbers. So let's say that if we take n equal to 1 and t equals to 1, if we do the substitution, we actually mean that it simplifies to for every x in the real numbers, for any integer n, there exists some 1 less than k less than capital N and some h inside integers, such that this k times x minus h is going to be 1 over n. So since these two are integers, and we have specified that this k has to be non-zero, we can translate this inequality into x minus h over k is less than 1 over h times 1 over k times n. So we can see that this actually gives you the distance between x to a rational number. And we can control the distance using the size of the denominator. And this is known as the Dirichlet's theorem on rational approximation theorem, or like Dirichlet's approximation theorem. You have a rational, like you can pick any large denominator, and when x is a irrational number, you can always pick a numerator such that the difference between x and this rational number is less than 1 over the square of the denominator. That actually determines how fast you can approximate an irrational number. Okay, so we have proved the case of this claim when the point is the starting point of the lightning. And now we are proceeding to the general case. And before we work on the general case, we can take a break, I guess. And we can discuss any questions if necessary. Yes?
So why exactly did it mean that if you could find the rays are dense in some circle around the original point, that implied that it's dense in the unit square?
Oh, not actually. We are just working. So if we want to do the entire square, we have to pick any point inside the square and then do a proof on it. So we are just showing a special case where that point happens to be the starting point.
Okay.
Because there are some cancellations, and that actually just means that all we need is just to approximate a certain real numbers to an integer. But for the general case, the canceling doesn't happen. We need to approximates a real number to some integer plus another real number. So that would be something that is different, more general, and actually more complicated than the case we just discussed. And we are going to use a completely different method. The pigeonhole principle, although it sounds very straightforward, the steps required to set up and apply the pigeonhole principle is actually complicated. So yeah, that's like a purely number theoretical argument. That's how it is. And in the next section, we are going to talk about a completely different method that can still allow us to handle rational approximations. But we take a break first. And there are some snacks over here, and just feel free to take anything you want.
It's really got more by John. Sorry, I didn't really I apologize. When you go on 9.
Okay, I think there needs some explanation for the set ST, because that's actually crucial to the understanding between the connection between the algebraic aspect of the problem and the geometric aspect, because I get asked. So one of you asked me this question, and I'm going to clarify this again. Because this is also very crucial to the understanding in our entire next section. So we consider this to be the origin of the square. So the way we want to study this problem is to reflect the square as the light travels. So let's say that the light is traveling in this direction. So this is P0, and it's going this way. Hopefully it's a straight line. So after the first reflection, we need to draw a reflected square here. And this is hitting the vertex, and by some continuity argument, we just draw a square here. And you keep drawing. And what I want to say is that if we label some random point inside the original square, let's say this point is Q. And the point Q is going to have the coordinate x1 and y1. So here, this is the origin, 0, 0. And after the reflection here is that this is going to be Q prime. This is after the first reflection. And we need to keep track of these points as well. So this is going to be 2, 0. And because we only did a reflection like about x along the y-axis, along a shifted y-axis, this means that the coordinate for Q prime is going to be same y coordinate, but different x coordinates. And the x coordinate is going to be 2 minus x1, and y coordinate stays the same. And if we do the reflection again, so it hits this vertex, so the light hits this vertex, so we actually need to do 2 reflections at the same time. So it reflects here, and then it reflects there. So you can treat this as a symmetry, like a symmetry about this point. You sketch a line here, and then you do it. So this actually turns the y coordinate into minus y. So this becomes 2 minus x1 and minus y1. And then we know that this is 2. So what this gives? So this actually gives something. So this is 2 minus x1, and then if we do the reflection here, this is going to be 2 plus x1 and minus y1. So when looking at the image of those points after reflections, we don't need to care about the actual value of the integer between it, but we just need to know that it's even. You can prove this by induction, but the fact is that you don't need to look at the the integer before it, it's certainly going to be even, but all you need is to care about the sign before the original coordinates of the point. When the sign is minus, you know that there's like a reflection that is not cancelled out. Same for x and same for y. We can see that this point, this is q prime prime. We can see that this point, at this point, you actually like, it reflects along the x-axis and both along, it reflects like horizontally and vertically, so that there are two minuses here. And if the reflection gets cancelled out, you only have the pluses. So using this principle, and we can generalize, we do some induction. It means that x1 and y1 lies inside the set St. If and only if there exists some time greater than t, and there exists some integers mn, such that the point is going to be, say, at this certain time, x0 plus vx times t. That's the x coordinate, and y0 plus vyt, that's the y coordinates. So the x coordinate, well, it's going to hit a reflected image of the original point. Say, if it hits q, then it's going to hit hits one of those kind of q primes, like one of the reflected image, because we did the reflection of the square and apply the law of reflection. So it hits the point q if and only if it hits some image after reflection. And the image after reflection, we know that the integer before it is going to be some even integers, and it hits either the cancelled reflection or the reflection that is not cancelled. So it's going to be plus or minus, because it's either like it's, so this is the minus case. So it's either in this manner or in this manner. So it's plus or minus x1, and for the y coordinate, it's the similar reasoning. It's plus or minus y1. And the plus or minus here are independent from each other. So when this is plus, it's also possible that this is minus. Yeah. This is just a sufficient and necessary condition. This is if and only if, but for our study, we can just focus on the plus case. So we can remove this if with if and only with this double if with a single if. So this becomes a sufficient condition. Because discussing the minus case is actually making the problem a little bit complicated, but we can just work with one case and then use the sufficient condition to get our desired results here. Any problem with this? So what we want to prove here is that the points are dense. The points are dense, it means that if we pick any point, for any of, say, xy inside the square, the unit square, for any of these points, there exists some x1, y1 inside the st. Also for any t greater than 0, and there exists a point inside the set, such that the distance between those coordinates are all less than epsilon. So this is what we want to prove. And from the condition here, we know that it suffices to it is enough for us to prove that it's hitting the point. It's going to approximate the point in this manner. So this x1 and y1 can be something that is not reflected. So we work with the plus. We work with the sufficient case. So first we have x0 plus vxt is equal to 2m plus yes, the integers, plus x1 and x0 plus vxt equal to 2n plus this is y0, so y1. And then these 2 points satisfies the inequalities. And we can just put this condition, we can combine these 2 conditions so that we can get another inequality as how we did like when this point is x0 and y0. So
How about VYT?
You have VXT and VXT.
oh sorry, yes, that should be v1. Yeah, that should be v1. So x1 minus x and y1 minus x. If we do the algebraic operations and simplify eventually, you get that this is equal to vxt minus 2 times n minus x minus x0. And this is going to be vy times t minus 2 times n minus y minus y0. So we know that this needs to be less than absolute. So what we want to do is to ensure that these 2 quantities, the absolute values, need to be less than some absolute. So for some reason we call this, say, or we can write it in another fashion. We just leave the integers in the end. So this is x minus x0 minus 2 times n, and y minus y0 minus 2 times n. So what we are doing here is that we are trying to make these 2 quantities, isolate these 2 quantities, approximate even integers. And this means that we can just forget everything above. We can just look at this quantity here. Because we can get rid of x1 by the following transformation. So as long as we can make these quantity as small as we wish, we are done. So what we are doing here is that we introduce the number. Let alpha be e to the pi I. We got some complex numbers coming to our plane. So this is v of x, vxt minus x minus x0. And we have beta is another complex number. vyt minus y minus y0. So if we look at these 2 numbers, when this quantity is very small, it means that these 2 quantities are approximating some even integers. So when these 2 quantities are approximating some even integers, these 2 complex numbers should be close to 1. Because we know that e to the pi I is equal to minus 1, but e to the 2 pi I is equal to 1. So on and so forth. So all we need is to find some t such that those 2 numbers can approximate 1. So we have just transformed this problem into some problem of analysis, in particular in analysis involving complex numbers. So we can forget about these. And then once we have this, once we can make both of these numbers sufficiently close to 1, we have our claim. So now we introduce the function f of t being equal to 1 plus alpha plus beta. So if we just do the absolute value inequality, or just look at this problem in the complex way, we know that these are certainly 2 complex numbers with the unit length with modulus 1. Because those are real numbers, this is having modulus 1. So this is the real axis, this is the imaginary axis. So we want to understand what f means. So let's say that this is the, so we first do the addition of 1. So this is 1 here. And then we add alpha. So this is going to be some angle, 1 plus alpha. And finally, we can draw another number here. And this is going to be 1 plus alpha plus beta. So this is the value of f. It can always be, like the value of the function can always be described by the picture. So in order for alpha and beta to be close to 1, we hope that this thing can be stretched to the real axis. So we want to stretch this line segment as long as possible. And the way we can stretch is dependent on t. So what I am trying to prove here is that alpha and beta will be close to 1 whenever when the function f, when the length of f is approaching 3. The length of the function is just the distance between this point and the origin. And when the distance is getting close to 3, this alpha should be something that is close to 1. And this beta should also be something close to 1, so that this becomes a line segment of length 3. So it's approximating line segment. So this is what we have here. And when the modulus of f is approaching 3, the line segment should look something like this. So maybe there are some tiny rotations, but the whole thing is going to having a length of, say, 3 minus delta. So it's only going to approximate. And we can actually prove this. We can actually prove this theorem. And the way we are going to prove this theorem is by considering an integral expression. So the lemma, a key lemma we are going to use is that when g of x, when g of u is continuous and non-negative, in some set omega. This is just a general set in the Euclidean space. Then this limit and the integral is over omega. And this is a volume integral. If we integrate over the volume of the set, and the integrand is the kth power of g, and we take the 1 over kth power here, and we compute the limit. This limit is going to be the maximum. It's going to be the maximum of the function g. So that will be, say, x inside omega and g of x. You can prove this using Squid's theorem and using the continuity of functions, but for the one-dimensional case and for the discrete case, so when g is on sequence, you add the sequence up, and then you add a kth power of a sequence up, and then you take the 1 to the kth power. If you take the limit, you get the maximal element of the sequence. And that is actually one of your analysis 1 homework, and sometimes it appears in the exams as well. Yes, but this is just a generalization of that argument. The point is that we can compute this integral, and then we get the maximum. We get the maximum. So that's the idea of the proof. Like, if we can prove that when g of x is f of t, and we consider the integral of t to, say, t1. So, and we want to make this t1 as large as possible, because we want to find a time greater than t. And this t1 is just the upper bound. We can make this as large as possible. So when we are actually doing the proof, we are considering this quantity, say raised to m power dt. And for certain reasons, we have some factors. We divide this thing by the length. We're actually considering the average value. And we do the 1 over n power. So the idea is that we want to take the limit here. We will eventually prove that this limit tends to 3. So this means that the function f can be as close to 3 as possible, and that's the actual way we prove the entire theorem. And I have the full proof of the theorem in my written notes, and I guess it will be too time consuming because we only have like half an hour left. So what I'm going to do here is I'm going to give you the proof of this level, which actually gives you a fashion of like why analysis can be applied to number theory. That's the trick. I'm going to prove this. And the higher dimensional case can be generalized without too many difficulties. So we just work with the one-dimensional case where omega is an interval. So this is the g of u and du, and g of u is raised to k power. And for some convenience, we just let the capital N denote this maximal value. So by some Square's theorem, we know that this thing is immediately less than b minus a times m to the k power. So this is one side of the inequality. And for the other side, by continuity, suppose that, because we know that continuous functions, they always attain the maximum and minimum. So that's I think they call it the extreme value theorem. So if g of c is equal to m for some c inside the interval, by the continuity, for every epsilon, there exists some interval, some subinterval of AB, such that this g of u is going to be greater than n minus epsilon for it's going to be greater than n minus it's going to be greater than 1 minus epsilon times n for u inside I. So that's just the argument followed from continuity. Like if the function is large at a point, then the function is going to be large near the point. That's what's happened when g is continuous. So if we plug this in the quality, we get that this whole thing is going to be greater than 1 minus epsilon times b minus a times 1 minus epsilon to the k power, and this thing is b minus a, and this is m to the k power. So we effectively have these two inequalities. And what's going to happen is that we are going to take the 1 over k power on both sides. So if we take 1 to the k power here, we get this 1 to the k power. And the k power here is going to be cancelled. So this is times m. And this is 1 over k power, and this is 1 minus epsilon. So now we are actually ready to take limits. For a fixed positive number, let's say 2. So 2 raised to the 1 over k power, when k goes to infinity, it goes to 1. So this goes to 1. And this thing goes to 1. Which means that the quantity, the limit here, is going to be greater than 1 minus epsilon times m, less than or equal to m. And because this epsilon can be arbitrarily small, we can let this epsilon goes to 0. So when it goes to 0, the whole thing is equal to m. And that's how this theorem is proven. Yes, that's the kind of argument in analysis. And yeah, that's the idea about the reasoning behind here. And for proving this f, I have detailed the steps inside my notes, and you can read my notes later on. And I think that actually finishes the talk today.
Hello, everyone. This is to continue from the actual talk. We didn't really finish the entire talk, so I will be finishing the remaining bits using the Zoom meeting room. So what we are left with is that we want to prove that if Vx and Vy are z linearly independent real numbers, then we want to show that for every xy, for every point inside the unit square, and every t0 greater than 0, we can always find some little t greater than t0, and some integer m and n, such that these two inequalities are satisfied. What this means is that we can really, which means that for every point inside the square, and for every time stamp t0, we can always find a point that is hit by the light after t0 seconds that is arbitrarily near the point we have chosen here. So to prove this theorem, we can transform this problem into a problem concerning the complex exponential function. We know that e to the z is 1 if and only if z is a multiple of pi, a multiple of 2 pi I. It's an integer multiple of 2 pi I. So what this means is that this approximates this quantity approximates 1 if and only if alpha is close to some integers. So using this principle, we can transfer our task here into the following. If we define alpha to be e to the pi I times vxt minus x minus x0, and beta to be e to the pi I vy times t minus y minus y0, then we see that alpha and beta are close to 1. If and only if the exponents approximate some even integers. So this means that we hope to choose some t such that both of these quantities approximate 1. And we can achieve this by constructing the following function. So if we interpret the meaning of this function in the complex plane, that has a very interesting geometric meaning. So let us denote our complex plane, and we let this to be the point 1. And if we consider complex numbers as complex vectors, then those those addition of complex number can be thought as vector addition. This means that we can add an alpha unit of vector, 1 unit of vector here to obtain 1 plus alpha, and we can add another bit of the vector, say in this direction, to get 1 plus alpha plus beta, which is equal to f of t. And if we want both, and we know that when alpha and beta are close to 1, when they are close to 1, the function f should be approximately 3. And the modulus of the function should also be approximately 3. And from the geometric argument, we can also see that if f of t, the modulus of f of t is close to 3, then both of alpha and beta are close to 1. And since due to our previous analysis on the impact of alpha and beta being close to 1, we know that if we can make them sufficiently close, we can prove our theorem. We can prove this approximation theorem. So both of them are close to so both of these quantities are close to 1. And we can give a rigorous proof of this as well. Suppose that suppose otherwise, we can assume without loss of generality that alpha is not close to 1 enough. So this means that alpha is equal to e to the I theta for some delta less than absolute value of theta less than or equal to pi. Then we have the following. We use the triangle inequality to get that 1 plus alpha plus the absolute value of beta, which is equal to 1 plus the square root of the absolute value squared, which is equal to 2 plus 2 times the cosine of theta. Like this is after some manipulation, and you will obtain this term. And by our specification for the cosine, we know that this whole quantity is going to be less than or equal to 1 plus 2 plus 2 times the cosine of delta. And we know that when this delta is very small, well, say this is something that is very small, like smaller than pi over 2, we know that this quantity is going to be, this cosine is going to be greater than 0 but less than 1. This means that the whole quantity is going to be strictly less than 3. And because this delta is it's not like it's not an infinitesimal number, so this means that f must be away from 3. So by the contrapositive principle, we know that if we take the contrapositive of this proposition, we see that when f of t, the modulus of f of t is close to 3, then alpha and beta can be close to 1. And if f of t can be close to 3, like in the arbitrary sense, we can make alpha and beta close to 1 in the arbitrary sense as well. So after transforming this principle, we can now analyze how this function behaves. And the way we study this function is to study its kth power. So this principle actually relies on the following lemma. Let this function, let's say that we have a phi of x, and let this phi of x be defined on certain subset of say of the Euclidean space, and it maps to the non-negative numbers, and the mapping is also continuous. So if we have this assumption, then we can take the following limit. If we take the following limit, we should obtain the maximum value. So this gives you the maximum of the function inside the set omega. So this is a maximum, not a supremum, because well, we assume that this is a closed bounded subset. So this is closed and bounded. So if we have these assumptions, then we should know that this limit actually gives you the maximum of the continuous function. And because we know that in a closed and bounded set, a continuous function always attains its maximum. So this is why we have a maximum here, not a supremum. And we can now start doing the proof. So if we do the squeeze theorem, we know that the whole function will be bounded by the maximum. So let m be the maximum. Then we have the following. And this is m to the pth power and raised to the power of 1 over p. So this gets cancelled. And if we take the limit, this actually tends to 1, because we know that this set should have a positive volume. So this tends to 1. And as for the other side, let x0 be the point that attains the maximum. Then by continuity, we can always find some point. By continuity, for every epsilon greater than 0, there exists some neighborhood of x. Satisfying the following. This gives up the opposite inequality. So this integral is going to be strictly greater than the following. It's going to be greater than the integral over the subset U. So this neighborhood U must be a subset of omega. And the content inside is going to be m minus epsilon raised to the p power, and the whole thing raised to the 1 over p power. And this can be simplified to greater than, say, the volume of U raised to the 1 over p power times m minus epsilon. So if we take the limit as p goes to infinity, we see that this quantity tends to 1. So what we have, if we combine everything, we see that m minus epsilon is going to be less than the limit infimum of the quantity we are discussing, and it's going to be less than or equal to the limit supremum of the quantity we are discussing, the 1 over p power of that integral, and the whole thing is going to be less than or equal to m. And because this epsilon can be arbitrarily small, we can make this epsilon go to 0. So we conclude that this lemma is proven. So the way we prove that this function f can approximate 3 is by applying this lemma to f. So if we throw this function f into we take the absolute value of f, and then we set phi to be that function and omega to be that interval, we can show that this limit actually tends to 3, and this actually solves the problem for us. So what we do now is that we investigate the power of the function, and instead, we investigate the kth power. So let f raised to the kth power be defined as follows by the principle of by the generalization of a binomial theorem to the kth power. We have the following. So it's a sum over 2 indices, R1 and R2. And the sum of those indices must be less than or equal to k, because we are raised to the kth power. It's going to produce a polynomial of the kth degree, and the degree is given by the sum of the coefficient, sum of these two numbers. And well, if you compute this very carefully, you can actually obtain an explicit expression for the sequence CR. It's going to be k factorial over R1 factorial, R2 factorial, multiplied by k minus R1 minus R2 factorial. But we don't actually have to care about the actual value of this number, but we just need to make sure that this is actually a real number. And so we see that this is actually the kth power of the function f itself. But what we want is to take the power of the absolute value. So we consider the quantity f to the 2kth power. So the interesting bit about taking even power is that we can always write this as the power of f to the kth power times the power of f conjugate to the kth power. And if we play a little bit with the term, we obtain the following. It's going to be R1, R2, and we also have the other term, R1 prime and R2 prime. CR1, CR2, CR1 prime, and CR2 prime. And the whole thing is multiplied by alpha R1 minus R1 prime and beta R2 minus R2 prime. And if we integrate the whole term in the interval from t0 to some large number t, then we are going to arrive at the following. So we copy the whole term here because they are still the same. And we integrate the inner term. Remember, alpha and beta are functions of t. So to study how this integral behaves, we can look at the formula that t0 to t, when e is raised to the power of, say, I times lambda times t. So we know that when lambda is 0, this integral is exactly equal to the length of the interval. But when lambda is not equal to 0, we can use the rule for the exponential function to obtain e to the lambda I lambda t minus e to the I lambda t0, the whole thing divided by I times lambda. And this is the case when lambda is not equal to 0. And interestingly, when lambda is not equal to 0, the whole term, this is actually bounded by 2 over the absolute value of this quantity is bounded by 2 over the absolute value of lambda. So when lambda is not equal to 0, this thing actually vanishes. This thing, when divided by the capital T, actually tends to 0. So we want to distinguish these two cases in the above expression. So we know that when R1 and R2 are both equal to R1 prime and R12 prime, respectively, the whole the integral is going to be evaluated to t minus t0. But we want to know the converse, whether this is possible when R1 and R2 are not completely equal to R1 prime and R2 prime. To investigate this situation, we look at the following. We can look at the following explicit expressions. So alpha 1 R1 times beta 1 R1 being identically equal to alpha to the R1 prime and beta to the R2 prime. So if we have this identity for any t, we effectively means that, like, after some transformation with the definition of alpha and beta that we can see here, we find that this is equivalent to saying that R1 minus R1 prime times Vxt minus x1 minus x0 plus R2 minus R2 prime and Vxt minus y1 minus y0, the whole thing is actually belonging to the set of even integers. And this actually implies that because we can make t to vary continuously, if we combine everything and this is a linear function of t, if we combine everything and the coefficient of t is not 0, then this function can actually take any value, which includes the value that are not even integers. As a result, we hope to ensure the coefficient for t must be 0. This means that R1 minus R1 prime times V of x plus R2 minus R2 prime times Vy is equal to 0. Because we know that R1 and R2 and R1 prime and R2 prime must be integers, these two differences must be integers as well. But because we know that Vx and Vy, well, from our assumptions at the beginning, these two numbers are linearly independent over integers. So this actually tells us that R1 is equal to R1 prime and R2 is also equal to R2 prime. So this means that this t minus t0 case can only happen when R1, R2 are both equal to R1 prime and R2 prime respectively. And in all other cases, we have the second case, which gives you a bounded term. So using the big O notation, we see that the original integral satisfies the following. This is equal to so this is the case when both the R and R primes are equal to each other. So this is CR1, R2 squared, and the whole term squared. And this is going to be multiplied by t minus t0. And the second term is going to be some bounded quantity. And this bounded quantity does not depend on t. So this is going to give you some remainder. And this remainder only depends on k, and it's going to be bounded. So it depends on k and t as well, but the point is that this remainder is going to be less than some ak, and this constant only depends on k. So if we take the limit as t goes to infinity, we have the following. So the limit as t goes to infinity, 1 over t times this t0 to t integral. Okay, I think this should be lowercase f because that's how we define it. So if we take the limits, we are going to arrive at the following quantity. So, well, we know that this is a constant, and we hope that this, because of the principle that we have before, we hope that this this quantity on the right-hand side should be something that is related to 3 to the 2k power. So how can we investigate this? We can use the following integral formula. So when the range of integration is from 0 to 1, the quantity e to the 2 pi I times x times y integrated along x is going to be equal to 1 if x is 0, and the whole thing is going to be 0 if x is some integers, that is if y is 0 here, and here if y is a integer that is not 0. So if we use this formula repeatedly, we have the following. So R1, R2, CR1 and CR2 squared is again going to be equal to R1, R2 and R1 prime and R2 prime. CR1 and CR1, CR2 and CR1 prime, R2 prime. And the whole thing is going to be integrated about along 0 to 1 e to the 2 pi I times R1 minus R1 prime over the variable u times the integral of from 0 to 1 e to the 2 pi I times R2 minus R2 prime over v. And if we combine the expressions, we will eventually arrive at the following double integral. And the integrand being 1 plus e to the 2 pi iu plus e to the 2 pi iv. This is just follows from the definition of the kth power. So raised to the 2kth power and du dv. So we know that this quantity, if we take the limit, so we know that the function inside, let's call this function guv. And from the triangle inequality, we know that this function is certainly going to be less than or equal to 3. And we know that this maximum is attained when u and v are equal to 0. So this means that the maximum of g is going to be 3. As a result, the following quantity. So if we raise the whole quantity by 1 over 2kth power, we should obtain 3 here. So if we combine everything, we have the following results. If we take the k limit outside, so if we take the k limit outside and then we take the t limit inside, and we have ft, absolute value, raised to the 2t power, and then we raise the whole thing by 1 over 2k power, this limit actually goes to 3. So to see how what this means is we can do the following. Suppose that f of t is going to be less than, say, 3 minus delta for every large t, say for every t greater than t0. This actually means that the whole thing, say the 1 over t, t0 to the to t and f of t raised to the 2kth power, the whole thing is going to be less than t minus t0 over t times 3 minus delta to the 2kth power. And if we throw this expression into the above expression, we find that the whole thing, this means the whole thing, 1 over t, 0, t0 to t, and ft raised to the 2k power. This means the whole thing, 1 over 2k. If we take the limit, we don't have to take the limit here, but this actually directly means that the whole thing is going to be less than or equal to 3 minus delta. But we know from the definition of the limit formula here, we know that this whole thing is going to be invalid when this t without 0, when this t variable is large enough. As a result, we reach a contradiction. This means that, so we know that the contradiction can't be true, so we look at the negation of the statement. If we look at the negation of the statement, we see that for every t0 greater than 0, and for every delta greater than 0, and there exists some t greater than or equal to t0, such that f of t, the absolute value, is going to be greater than 3 minus delta. So this means that the function f of t can be close to 3 in this arbitrary sense. And this effectively proves the theorem, proves the proposition we have at the beginning. And this proposition tells us that the set of points passed by the light are dense, is dense inside the square. And we can also generalize the arguments we presented here to obtain the following approximation theorem. And this theorem is by Kronecker. So this is Kronecker's theorem. So we only work with the two-dimensional case because we are only discussing the reflection inside a square. So let the function, so if we generalize, we have a n-dimensional theorem. So let x1, x2, all the way up to xm be a sequence of real numbers such that they are linearly independent over Z. And we also pick another sequence of numbers, alpha 1, alpha 2, all the way up to alpha n. Be some arbitrary real numbers. This corresponds to the quantity x1 minus x0 and x minus x0 and y minus y0. And so under these setup, then for every epsilon greater than 0 and for every t0 greater than 0, there exists some number t greater than t0, and there exists a sequence of integers such that the inequality is going to be valid for every m, for every small m. For m running from 1 to the capital M. So this is the Kronecker's theorem, and this is the Kronecker's theorem in the n-dimensional form. And since we know that the Dirichlet's approximation also has an n-dimensional form, we can actually apply those theorems to study the generalization of our square problem. So in our talk, we only discussed the square, which is the two-dimensional case. And with the Kronecker's theorem and the Dirichlet's theorem, we can study the m-dimensional case as well. So so if we accept this generalization, we see that in an m-dimensional hypercube, if we shoot a beam of light inside, the ray will follow a loop if and only if the velocity component, each coordinate component of the velocity of the light are going to be linearly independent over integers. And also, if they are not linearly independent over integers, so the periodicity happens if and only if those velocity components are linearly dependent over integers. And if they are not linearly, so if those velocity components are linearly independent over integers, then we are going to reach a situation where all the points hit by the light are going to be dense inside the m-dimensional hypercube. So this actually summarizes our talk. And now we can discuss some of the advanced applications of the approximation theorems we obtained well, of course, we are not going to prove those theorems, but it's worth mentioning them. So, applications. And since we are discussing in the context of number theory, I prefer talking about some number theoretical applications. So let this quantity, let pi of x be the number of primes less than or equal to x. And let this Li of x be the integral from 2 to x. Inside we have the reciprocal of log. This is known as the logarithmic integral. And the prime number theorem states that if we divide pi of x by Li of x, this tends to 1 as x goes to infinity. So this means that this Li of x is a good candidate for us to approximate pi of x. But however, if we play with, if we apply the Dirichlet's theorem, we actually can prove that this approximation is not that good. Is not that good. So the Dirichlet's approximation theorem tells us that there exists some constant greater than 0, such that there exists such that for every capital X, for every x0 greater than 0, there exists some tiny x greater than x0, such that pi of x0 minus Li of x, x0 is greater than k times x0, 1 over 2 power and log x0 over log of x0. And we take absolute value here. We don't take absolute value here. And yes, this should be x without 0. That's a mistake. And there also exists a y greater than x0, such that pi of y minus Li of y is going to be less than minus k times y over y to the 1/2 power times log y over the logarithm of y. So what this means is that these functions, they can be very far away. The function pi of x can be very far away from Li of x in both positive direction and both in the negative direction. So a more simpler result is that pi, and this actually implies that the function pi of x minus Li of x changes signs infinitely as the variable x goes to infinity. The reason is that we can put infinitely here is because we can always, because the number x0 can be arbitrarily large. As a result, we have the following sign change theorem. So this is the application of our theorem. And regarding the topic for our talk, the motivation comes from a textbook by Hardy and Wright. So I will put the reference here. So in their textbook, they talk about the specific details concerning the reflection of the light in the rational approximation section. So let me write the name of the book. And since this is an old textbook and the name is quite common to any textbook about number theory, it's pretty likely that you will stumble upon an introduction to the theory of numbers by some other authors. But here I need to emphasize I am reading the book titled An Introduction to the Theory of Numbers by Hardy and Wright. So these are two important mathematicians in the early 20th century. And this is actually a very nice book. And another book, which I take the proof of Kronecker's theorem from, is by Tishmash. And the book is called The Theory of the Riemann Zeta Function. And you are not mistaken. He is applying the rational approximation theorem to study the Riemann Zeta function. And that finished the talk. And thank you for listening to the talk live and also for watching the video online. Thank you very much.